So, I thank Arvind Shilpak and all others for inviting me and visiting two premier research institutes, IIT Tirupati and IISER Tirupati. The second one is our sister institute. I would make it much more simple. And well, since I am from the math side, I will probably try to attract more mathematics people actually. Physics people probably will have to tolerate me a little bit more. Okay? And in that I will tell the story of KRP also in the middle. Yes. So, let us start. So, when we study measure theory, study probability theory, we do it with a Kolmogorovian triplet. So, basically we give the students this kind of thing, that let omega be a set, maybe finite, maybe countable, maybe countably infinite, maybe uncountable, anything, which we call as the sample space. Then a set E, which is called as the set of events. These are actually subsets of the sample space, and along with a probability distribution P. Now, those who does a little bit more, who studies a little bit more on probability theory will immediately point out that this set of events is actually a sigma algebra, and altogether this forms a triplet or a measure space omega, set of events E, and the probability measure P. All three makes a probability space, which is called as the Kolmogorovian triplet. Now, what I want to do is that, or what KRP wanted to do, and other people also like him wanted to make it a non-commutative probability theory. So, there are couple of things when it comes to non-commutative things, why we do this, why do we do that, and etc. These things falls under the domain which I say that is in the foundations of physics. So, we do not generally go in the details there, but let me say the outcome or the postulates what I will do for the non-commutative part. So, here what I would do is simple. The sample space will be replaced by a Hilbert space, which is a complex separable Hilbert space. This may be of finite dimension, in that if it is finite dimension, then it is very simple. This is CD, when D is the dimension of the space. If it is of infinite dimension, then you have many interesting spaces. For instance, we had two lectures, effectively two lectures on Fock spaces. So, they are kind of second quantization of these things upon some Hilbert space and so on, or if you want you can take the L2 spaces also, they will do that job, or if you want more exotic things, then L2 of, as Professor Usha Devi was mentioning today morning, L2 of R plus, but then you have different types of troubles which you have to take care of the things there, because for instance, some people call this thing as not a right Hilbert space, but a rigged Hilbert space, but those are the technicalities, we do not bother about those things. For me, it is a Hilbert space, which means it has an inner product, valid inner product, and all that, under which it is closed and all that. There is a norm also, standard norm. The set of events are replaced by this P of H, which is the set of all projections. projection operators. This will eventually replace the set of events, but I am not going to venture in that direction, because this again falls under the domain of foundations of quantum mechanics. So, that is a slightly murky area, I do not want to go in that, but I have to make the triplet ready. Now, the most important thing is the probability distribution. This is replaced by a object called rho, which is positive semi-definite Hermitian operator, Hermitian trace class operator with trace of rho is equal to 1. So, the triplet for me is the following: Hilbert space, which is analogous to the sample space, a set of projections which is in this space, which is analogous to the set of events, and probability distribution is replaced by rho. Now, we call this rho as state. So, physicists always keep on talking about what that consider a state rho. From math side, it is very simple. It is a positive semi-definite Hermitian trace class operator with trace is equal to 1. Trace class means, those who are not very familiar, if you go for the infinite dimension, then you may have a difficulty in defining a trace in the appropriate algebra. So, you need to have these operators which are of the trace class. If you are working on the finite dimensional system, like most of the quantum information theories do, which means you are working on C to the power d, which means it is actually a matrix algebra, then there is a valid state, a valid trace. So, you do not have to bother about it at all. Okay. So, this is my quantum probability space. Yeah.
So, set of events, in a generalization, I would have taken the set of completely positive ones.
No,
or
that
set of cross operators.
no, it is not exactly. Okay. So, yeah. Yeah.
Is there a set of properties that like countable additivity or something, or does it even make sense, or is just a trick?
No, it makes sense. No, it makes sense actually, but I do not want to go in that technical direction there. In fact, there are even zeroth questions are also there. Why do you bother about a complex separable Hilbert space? Why do you need it? I mean, you can remove the word separability from there. In fact, people actually worked upon this kind of a question in I think in the field theory like Regge calculus and things like that. People actually thought about it, but those things did not go too far. I mean, just like today morning somebody was pointing it out, the nonlinear Schrodinger equations, and there are different models are there. So, I do not want to go in that direction actually. Okay.
When you said in the beginning you want to make a non-commutative theory, which one of the three things you are taking?
We are taking matrices. I will come to that.
No, which one of the three things of the triad, which one of them you are tweaking?
All of them practically. The Hilbert space itself I am taking that, right. I will take the operators upon the Hilbert space, and operators are very much non-commutative in nature. I am coming to that thing in a minute also. So, you are very much right that there should be a non-commutative version also. Maybe maybe it is just quote unquote from Professor Rajaram Bhatt's paper, an old paper. So, when you take probabilities, you also study something called the random variables. And how do you define? Okay, so for time being, let us say I am not bothered about the situations when things are of infinite dimension. I want to keep everything upon the finite dimensional side. Now, if you have a random variable x, which is taken from the sample space to real or whatever the space the images are, how do you generally take the things? The expectation of x is taken as summation of pi xi when these x's are of taking the finite number of values only. So, I take the space sample space omega is equal to let us say 1, 2 etcetera up to n outcomes are there, and I have these probabilities p1, p2 etcetera pn of each outcome, summation pi is equal to 1, all the pi's are greater than 0. And then if you have a random variable x, it will take the values x1, x2 etcetera xn, and then the expectation will be of the form I is equal to 1 to n pi xi. Okay, or maybe I should write it as xi pi just for my whim. I write it in this way that x1, x2, xn and p1, p2 etcetera pn. I can do it. These are these are nice products, and I take the this is the trace of this whole thing. I would call this as the expectation of x with respect to this probability distribution p whatever it is. Now, in the non-commutative setup also I should do the something similar. So, these x's are observables, these are observables which are basically the maps from the sample space to the real line. Let us stay to the real line itself. The analogous thing of observable is what is called as x is my bad, x is the random variables, and the analogous thing is what is called as the observables. The observables are written by the same notation I use x. These are all Hermitian operators. And the expectation of x upon a state rho, which I write like this, will be nothing but trace of x acting upon rho, or in physics people like to represent it by this notation also. So, this is my cheat sheet for my maths friends, that for me a state is nothing but a positive semi-definite Hermitian operator. I am taking only finite dimension, that means I am safe. We are only bothered about matrices. In infinite dimension you have to think a little bit more how it works out, and these are the dictionaries which will translate the things between one to the other side. So, some more notations. That is exactly where the non-commutativity comes up. For instance, you can also see the one situation. Suppose you have two random variables x and y. How do you take the covariance of that? It is expectation of x into y. But here, if I take expectation of x into y, I can only take observables as to be Hermitian operators. Now, the x into y, x is a Hermitian operator, y is an Hermitian operator, their product need not be an Hermitian operator. So, when you want to actually do the correlation, you need to actually not go for x into y, you take x into y plus y into x divided by 2 and take the expectation of that. Now, this is an Hermitian operator. So, these are the places where non-commutativity seriously plays the role here. Okay. So, some more notations. Suppose you have two systems. So, whenever physicists talk about, so let us have a particle which is moving in some system, then you should always recall that, which means there is the system there is the whole thing space is actually a Hilbert space, maybe finite dimension, maybe infinite dimension. A particle is nothing but this kind of a positive semi-definite Hermitian operator, trace class Hermitian operator, which is equal to 1, roaming around in something, interacting with something, and all the things. Some more cheat sheet. So, when you have two spaces, two sample spaces, I can drop, actually I can drop this set of events because I am not going to discuss more on that thing. So, if you have omega 1 is a sample space, omega 2 is another sample space, then their combined sample space can be written as omega 1 cross omega 2. I do not want to go for explain it to the physics people, because the math students already know how to go for the product measure and do whatever the calculations there. But yes, it is just you are doing a product measure upon the product space there. Rather, I am interested what happens here. So, if you have two systems H 1 and another system is also H 2, then the joint system will be represented by H 1 tensor H 2. Now again for maths and physics people actually together, that is whenever we say that it is a tensor, the way I learned my tensor product was upon the in the theory of modules, and it is about using this universal property of the tensor products, and all the things were defined there. The same thing holds here also, but I should write it exactly what the algebraic tensor product means. So, consider the situation that I have two matrices A of I j, it does not matter whether these objects are square or rectangular, because and I have another matrix B, then I can take the tensor product as A tensor B as a matrix which is of the form A of I j into B, and you are taking the block matrix of that type, sorry. Okay. So, this is my tensor product. Now, those from the math side actually can go back and check that this is actually a valid tensor product, and using that the universal property, you can see that rest of the tensor product structures are satisfied here and all that. Okay. This will be very useful because of a very curious thing from at this point, which will change from the classic, which will actually use the non-commutativity properly. You see, what are the states on this kind of systems are? Of course, I have the states which are of the form rho 1 tensor rho 2, where rho 1 is a state in H 1, rho 2 is a state in H 2, but they are not all. There are states which are up in this space, which I cannot write it in this nice fashion. I should give an example. Consider the situation in which your H 1 is equal to H 2 is equal to C 2, and you take the state rho as half of 1 0 0 1 0 0 0 0 0 0 0 0 1 0 0 1. Try to write it as a tensor product of two states, you cannot write that thing. This is an exercise I can give it to the students. Actually, it is even worse. Not only I cannot write it as a tensor product of two states, I can't even write it as a convex combination of the tensor product of the states either. So, that means I need some kind of a naming here. So, a definition, a state rho in H 1 tensor H 2 is said to be separable if it can be written, if it can be written as convex combination of states of H 1 and H 2. That is, I can write the rho in this way, summation of I is equal to 1 to let us say k some p I rho 1 I tensor to 2 I, where rho 1 I is a state in H 1, rho 2 I is a states in H 2, p i's are all greater than equal to 0, summation of p I is equal to 1. Oops. Oh, you have a nice board actually, nice smooth thing. Let me just, and if rho cannot be written, in this form, we call it entangled. And this is the most important thing, probably one of the most important thing in quantum theory, that the existence of these entangled states. The words which you hear about, the buzzwords, the quantum theory, quantum supremacy, quantum all the anything you add a quantum on this thing is due to this existence of this particular object called entangled things. And this is something which we teach in matrix analysis or in the modules to the students, that there are objects which cannot be written as just a product combination of the product of matrices. There are matrices which cannot be written as a combination of product positive matrices or vectors or so on. Okay. These are the particular things which gives you makes the difference between a classical thing to the quantum thing in this setup. This is not available in classical situation, and in quantum it is available. I should also point out that when I define the things as the positive semi-definite Hermitian operators rho with trace error of rho is equal to 1, I should also say that there is a very particular kind of states available which are of rank 1 projectors. They are called the pure states. So, let me add it here. So, state rho with rank of rho is equal to 1 is called pure state. Maybe I put it this side. For some reasons, we physicists like to use this notation called bracket notation, which are like which are the following. So, again consider the same situation, H is equal to C power D. I take a vector, let us say x1, x2, etc., xn in CD with the extra property that summation of xi mod squared is equal to 1. I denote this thing as psi. This is called the Kate notation of the things. If you do not bother about, if you want to think too much about that thing, consider it as a vector and a fancy way physicists like to put, but it is actually a projective of a vector which will come in later. Sometimes it is useful to remember, sometimes it is not. And by virtue of our previous thing, my rho can be written as the Kate of psi, bra of psi. Mathematicians would probably like to write it as psi and then psi star, which is actually the dagger of that transpose complex conjugate of that thing. So, this is a pure state which is a projection operator here. And obviously, there are situations which are called as the entangled state, which cannot be written in terms of convex combination of these things. Now, one natural question comes in our mind, that suppose I give you a state from any, I give you a Hilbert space, and that from that Hilbert space I give you a state. Can you tell that is it a separable or entangled immediately? It's a very natural question. There is an easy answer for this object, because you see one thing happens that if your state rho is a rank 1 operator, that is psi, then actually it will break it as psi 1 tensor with psi 2, where this guy is upon the Hilbert space H 1, this guy is upon the Hilbert space H 2. And if I there is something called taking the partial trace, that means upon removing one Hilbert space and keeping just the one other Hilbert space ready. So, if you do that thing, that means you trace out one of the Hilbert space components, then you get, let us say you do it trace out the second part of that thing, then you actually get it the first part, which is psi 1, or if you take the second one, the first one, then you get the second. The point is that if it is a rank 1 projection, in that case when you trace out one of the systems, you still get a rank 1 projection. On the other hand, if your state is not, if your state is entangled, in that case you do not get this kind of things. So, you get something which is not of rank 1, and that will give you a signature. Okay. Now, these are all perfect simple things in pen and paper. I can just give it to any student and I can tell that to find out that. But let us say what is going to happen if you do a little bit more complicated. So, take a so when I defined a state, I never said that the state has to be of rank 1. When I defined it of a separable or entangled state, I never bothered about whether they are of rank 1 or 2 or whatever the rank would be. They are called the mixed states. If it is not of rank 1, they are called the mixed states, and the mixed states, it is a difficult problem. In fact, it is so difficult, those who have done a little bit of complexity theory, it is actually NP-Hart problem. So, in other words, given this given an arbitrary Hilbert, two arbitrary Hilbert spaces and a random operator from that thing, is there an algorithm to prove that prove or disprove that whether it is an entangled or separable? The problem is NP-Hart. But on the other hand, you should also understand that these are the points, the entangled objects are the vectors or actually the operators which gives us something more useful than the separable things. The separable things are kind of classical, and these are the existence of these objects are actually give us the quantum thing. So, basically to identify these objects, we need to do a lot of hard work there. Okay. And they are the resources also in some way. Those who understand the resource, there is something called theory of resource. Those who understand, they are used as the resources. What I want to do now with this? Well, we are still, I am a mathematician, so I do not have to bother about how to find out in things in experimental lab and things that will give me an extra load of trouble. Even in pen and paper I can't do many of these things. So, but I can do certain things more from here. What are they? One single interesting thing is the following. Let me, as I said that I did not manage to prepare slides because I could not get enough, I mean I wanted to access everybody. So, I have to see a few things and tell it. Just give me a minute. Yeah. Okay. So, one question which was asked by KRP, actually not initially by KRP, the people asked a different question which is of the following nature. See, all the things whatever I have told right now, they are actually upon two systems Hilbert spaces H 1 and H 2, tensoring together. Of course, I can without difficulty I can extend it to any H1 tensor H2 up to Hn. That would not create a problem for me, but it will make it more complex. More complications will only increase. So, just keep it in mind. So, but even in two systems H1 tensor H2, this interesting object happened. People found out that these are of finite dimension, and I take the product vectors alpha I tensor beta I. Okay. I is equal to, let us say this, both of them are of dimension d. So, this is a d square dimensional space. I do not go up to the d square dimension, but rather I come to some dimension which is smaller than d square. So, I is equal to 1, 2 etcetera up to let us say k. I take this alpha I tensor beta. So, what I did, I took alpha I and beta I, and I also need a condition, they are orthonormal. Okay. Just give me a second. So, rather I give a small example actually that would make life much more simple. So, consider the situation H1 is equal to H2 is equal to C3. You have the standard basis, let us write it as E naught. Okay. For some reason I write it as 0, which mathematicians like to write it as E naught, E1 and E2 probably. They are the standard basis, and using this standard basis I am trying to write some vectors. So, these following vectors 1 by square root of 2, 0, tensor 0 minus 1, 1 by square root of 2, and the last one is 0 plus 1 plus 2 tensor with 0 plus 1 plus 2. Actually, we need to use so many of these tensor products. So, we generally physicists try to ignore it and just write it as a standard product here. The understanding is that these are the vectors are actually there is a tensor product between them. Now, take these vectors. What can you say about these 5 vectors? See, they are all kind of separable, they are kind of product vectors, they are all orthonormal. Because to maintain this orthonormality, I had to take care of this 1 by square root of thing, etcetera. They are not complete, because this space is of 9 dimensional space, we only have 5 vectors. So, why am I bothered about it? I am bothered about is the following reason, that with this state, with these 5 vectors have this interesting property that, okay, I have been given a 9 dimensional space and 5 vectors. I can always add one more vector, and one more vector. Gram-Schmidt orthonormalization is there always. Can I add can I add a product vector? Sorry. Can I add a product vector here of the form alpha tensor beta with this? Again an exercise, I can't do that thing. In other words, the orthogonal complement of the space formed by these 5 vectors, there is no product vector is there. I can't add one more product vector which is orthonormal to all 5 of them. There is a name of this type of vectors. They are called unextendable product basis. Unextendable product basis in the sense that there are product vectors, but I can't make them a complete product basis by adding one more product vector. See, in this space C3 tensor C3, I always have this product vectors 0, 1 and 2 I comma j is a product vector, and that is always forms a basis. But I am doing a cleverly somewhat I did not do, somebody else did that thing. These are Bennett, Brasher and various other people. They cleverly choose these 5 vectors and they cannot be extended. I can't add a 6th vector which is orthonormal to all of them.
Is there a formula for the number of non-extendable?
Very good point. So, that is what people actually try to do. The problem with this is that there is a minimal number which is possible actually. This is based on the Ramsey number of the graph. The best things it was initially done by Peter Shor and the same members of that group, and later it was properly formulated by 2 very famous graph theorists, Noga Alon and Laszlo Lovász. I think it was in Journal of Combinatorics or somewhere. They actually gave this minimal number, how many things can be done. Yeah. Okay.
Minimal number means like
how many? Suppose you are given a
size of a extendable.
yes, and not only in this case just 2 parties, then 2 Hilbert spaces. It can be of n. Yes. There is a minimal number possible.
No maximal
I
number.
cannot go for 4 here. Is that mean? What I mean, I cannot construct with the 4 vectors.
I can't.
At least minimum 5 vectors in array.
In the 3 tensor 3 you have to have this minimal and maximals are always 5, but in the higher dimensions this minimal number and maximal numbers changes actually, and in multipartite situation also it changes.
So, any estimate for maximal number or?
No, not that I know of.
If one is there because of your example, something like that can be constructed. I guess.
Which one?
Just nm minus 1 could be a maximal, but that's a crude estimate.
Yeah, but that is a very crude, right? I mean, if you take
What is there is no
no, I mean no, it's not actually as per I know.
Bipartite case, that B1 cross B2, then B1 into B2 minus 2 is a maximal one.
Okay.
Is always
Loose bound, yes. But given some number d1, d2, dn, I mean h1, h2, hn are there with the dimension d1, d2, dn, and then what is the upper bound actually is possible, what is tight bound in that I do not know. There is a minimal is there that comes from the Ramsey number of the graphs. Some combinatorial argument was there. Okay. Why did these people who are bothered about this kind of vectors were also somewhat it had a different story. That story is more physical in nature, so I do not want to go in that thing. Those who are from the physics department, they may be able to connect. So, they wanted to do the LOCC discrimination of product vectors, and you see if you have two vectors and if they are orthonormal to each other, then it is easy to actually do a discrimination. The question is that can you do it by local operation and classical communication? What they found out was that local operation means the operations upon the H1 and H2 respectively, or the operations which are of the form A tensor B type of operations. What they found out was that no such tensoring operation can distinguish these 5 vectors. If you want to do that thing, then you must have a vector which is actually not a product, but an entangled thing as one of the distinguishing apparatus or something like that. So, So, it is very curious that their product vector, they are orthonormal, they should be distinguished, but then there is something which is bothering or which is stopping, there is some physics which is actually stopping them to be distinguished. It is very unique object. The second interesting thing is again comes from the thing about entanglement. As I said that the way to find out entangled states is very difficult, but then there must be a there must be some nice operations to do that kind of things. So, without going in much details, because my time will be up and I will not be able to enter in the main point, is the following. So, eventually you are working upon H1 tensor H2, this kind of things, and you take a transformation T from B of H2 to B of H, okay, let me keep it as 2. What type of transformation you want? You want the transformation to be positive, just the positive. Positive means the positive operators here are going to the positive operators here, but not completely positive. This will come, this I do not want to explain what is that, but you can ask me a question, what kind of objects are there which are positive but not completely positive. These are like transpose is one such operation which is positive but not completely positive, which means the following. Maybe I can just tell it also, that the positives are things which sends positive elements to positive elements, but if you take the extension of those kind of things, B of H1 tensor B of H2, which is actually something similar to this, to B of H1 tensor B of H2, you take the transformation, do not do anything on the first part, do the operation only upon the second part, whether this object, this extension of this mapping identity tensor T is also positive or not. This is what is called as the completely positivity. If it is positive for every extension, then it is called as a completely positive. Simplest example which is not does not follow this kind of criteria is transpose operation. And in fact, there is a theorem due to Arvidsson, Stormer. It was there in the paper of Arvidsson and Stormer, but never explicitly written. It was explicitly written in Aronovich. That any transformation T from B of C2 to B of C2, or the T which are of B of C2 to B of C3, which maintains positivity, that means sends the positive elements to positive elements. I should also write the tree as B of C3 to C2, can be broken in this kind of way as a completely positive plus transpose composition with a completely positive map. In fact, what happens is that in the dimension 4 or dimension 6, by using transpose you can find out all entangled states or partial transpose. These objects have this nasty habit, their orthogonal complement have this nasty habit that they do not show, they are entangled and they are let us say d square minus k, they are actually entangled, they are positive under partial transpose. So, that means partial transpose cannot detect those kind of objects. So, they are these kind of states, these kind of objects are very useful for, and this is the only systematic way to develop, to give an example of this kind of matrices which cannot be written in this way and cannot be nicely found out. Where is, but I have not talked anything about KRP yet. So, let me come to the questions which KRP asked. KRP asked this question about this, he was fascinated with the problem of maximally unextendable product basis, and then he asked another question. Unextendable product basis in a sense gives you kind of a bound that in that space you are trying to increase the number of product vectors such a way that their complement does not contain any product vector. Can we do a reverse question of that? The reverse question is the following, that is it possible to have a space where every vector is entangled, but and that is of your maximum dimension. That is what he is calling as the completely entangled subspace. So, this is you take the Hilbert space H1 tensor H2, you take a subspace S of H1 tensor H2 such that every vector, or rather I should say that there does not exist any product vector alpha tensor beta in S. Okay. Maybe I should write it as H1 tensor etcetera up to Hk. In that case, I would write it as alpha 1 tensor etcetera up to alpha k belongs to S. Non-zero obviously, otherwise everything is trivial. Yes.
Sorry, that means that in that subspace taking superposition of any entangled state also
Will give you again entangled. Okay. See, it is a subtle.
Here isn't it not like that? I am little bit confused in the sense that if I try to extend this one in this from unextendable basis to
No, it is the same thing, but here you see, here we try to put more product vectors and make it the complementary space much more smaller. Whereas here we are trying to make more entangled vectors such that that space, if you make the linear combinations of them, they will still remain as an entangled object. That is tricky. That part is really the tricky part.
So, you can have linear combination of
Again entangled vector.
so that is not in general true.
In general, it is not true. For instance, you take this situation that H1 equal to H2 is equal to C3, 0 0 plus minus 1 1, 1 by square root of 2. See, you just add them, you get a product vector 0 0. So, it is not true in general. Okay. Now, is this object completely entangled subspace is a theoretical thought just only? Well, if I just take one vector, one entangled vector, and then take the span, that thing definitely it will be an entangled thing. So, there is obviously it is a non-zero object, it is a not vacuous things. The question is that can we have a maximal dimensions of that thing. So, here is the interesting result. So, let me see my slides now a bit, just a second. Just a second. Yeah. So, so the question here is the following, that what should be the maximal dimension of this kind of objects, and the theorem here is the following: the maximal dimension of S is, okay, assume that this is of dimension d1, d2 etcetera dk, then this maximal dimension of S is d1 into d2 etcetera up to dk minus d1 plus etcetera dk minus k plus 1. This is the maximal dimension. Okay. I think I have 5 more minutes, right? So, I will just try to prove this theorem in a short way and tell it exactly how.
So in a way, like this is quite big, so that thing should be quite small.
Which one?
The complementary part is
That is complementary part will be small, yes. The complementary part is exactly the d1 plus d2 up to dk plus k minus 1, right? It is a maximal of course, but there exists a space. And
maximum unextendable product basis is smaller than the maximum.
oh, right. If that is your question, yes, the unextendable product basis is smaller typically. Maximally it is. It's not maximal always. Yes. So I'll quickly give this sketch of the proof. The idea is the following, that I define a number n which is equal to I made a mistake, plus k minus 1, and the reason is obvious. So, I define the number d1 plus d2 plus etcetera dk minus k plus 1. Let us define this number as n, capital N, and I take a set of non-zero complex numbers lambda 1, lambda 2, etcetera up to lambda n belongs to C minus 0. Now, I also do a small technique which I mean mathematicians will be able to find out easily, lambda I square etcetera lambda I to the power dj minus 1. I call this whole thing as u of ij when 1 less than equal to I less than equal to n and 1 is less than equal to j is less than equal to k. So, this object I take my u and I take this kind of things, u of I1 tensor, u of I2 tensor up to u of I k. So, these are the vectors which I take from there, of course, for r is equal to 1 to etcetera up to n, okay. I to etcetera I is from 1 to n. Take the span of all these product vectors. Now, this is product vector, take the orthogonal complement of that thing. My claim is the following, that this orthogonal complement cannot contain any product vector. Why? If you have a orthogonal, if you have a non-zero product vector, so this is my space S. Now, if you have this vector v1 tensor, v2 tensor etcetera, vk belongs to S, of course, this is not equal to 0 and this is belongs to S, that means with respect to every such product vector, it should be equal to give me 0. In other words, for each product vector like this, there should be at least one component on which it will give me 0, because otherwise how it when I take the inner product, how it will be V I inner product with u I 1 into V 2 inner product with u I 2 etc. V k inner product with u I k. At least one of them has to be equal to 0 for each u 1 u I 1 u I 2 etc. u I k. Now you count how many, for each one you should get 1 0, and you count how many zeros are possible here. It turns out that because you have chosen a very strange number n is equal to d 1 to d k minus k this thing, you okay. So, let me write it in this way, that let us define E of I is equal to all those i's such that V of j u of I j is equal to 0. Okay. This is a subset, naturally a subset of 1, 2 etc. up to n, and you can actually do a little bit of counting and show that this number of E i's must be greater than equal to this number n, capital N, which means because n is equal to d 1 plus up to d k minus k plus 1, it must have at least one situation such that E k is equal let us say it is equal to 1 E 1. It must have d 1 more than d 1 number of non-zero zero components are there. That will create a problem, because you see you if you try to calculate the vector, then you will eventually find out that you are calculating a van der Waals matrix, and the van der Waals matrix will give you a 0 whose determinant is equal, it has to be invertible, and that is it is not possible. I mean it has to be equal to 0, which is not possible actually. So, that is in a nutshell is a slightly hazy way of telling things that this is not possible. So, in fact, there is no product vector here. Now, that is just only one side of the story. The other side is the following, that if you if you take the mappings on which tells the following way, that after all we are bothered about only the product vectors which are actually orthonormal. So, in other words, we are actually considering with projective Hilbert spaces like this, P of C d 1 etc., P of C d k, and their cross products there. If I take a map T from here to projective things C of d 1 cross up to C of d k, this map has an interesting name. Those who are from math side, they know that thing, that this is, I think this is what is called as the Segre embedding, right, that putting the products here. Professor Nagaraj probably will be able to tell more about this thing, and then you can actually show that the space which is of dimension this tensor, right, yes, which is of dimension this cannot have any product vector by using this Segre embedding. So, I can skip this part here, and combining these two things I can say that the maximal dimension of this entangled objects is of this thing, is exactly this. So, these are the two parts of the proof. Now, why? Now, you see what, of course, the last part I have used a bit Segre embedding, but the first part is eventually simple linear algebra and nothing more than that. Of course, one can ask the question why one should bother about this kind of constructions. Well, for various reasons this spaces comes in handy. One part which I do not know, and KRP actually spent quite some time, is about the coding theorems. That is one part. The second part is is that I can give some extra, I can relax the conditions upon these things. Since it is a there are multiple parties are there, it is not a bipartite, but a multipartite. I can say that and I am using the stringent most form of the separability, that is the product vectors, there should not be any product vector. Maybe I can use some slightly looser condition of separability, which I do not want to go, but maybe I can or I can give a condition of the entanglements that they should have something, the entanglement of some level beyond that. There is something called a Smith number computations of those things, and I can construct those kind of things. All of these have been used and worked for quite some time, and people looked at it starting from this paper of KRP. But the last one, which came just in this month of May, is the following. May I take 2 more minutes? Okay. So, it is a common sense that suppose I have 2 channels. Channels means like electricity, electric wires are also there, and you want to send some signal through that thing, maybe a current. If you send too much of signal, what will happen? It will burn, or probably it will not go, right. So, every channel has a capacity how much signal it can transmit. Now, the question is that what can you tell about the quantum thing? Well, quantum channels are what is called as a completely positive trace preserving maps in mathematics language. I did not define it, I did not get time to define it properly, but let us say a map which are of this B of CD to B of CD, which are completely positive trace preserving maps. These also have kind of a capacity. Now, you can of course ask me this question, see Arbi, you have told about this tensor product etc. blah blah. So, what is the quantumness? Can quantum give me something more about it? In fact, why not I take T1 D1 D1 and then T2 of the same kind of thing D2 C of D2, 2 different spaces, right. Can I, if I take the tensor product of these 2 maps upon of course the tensor product of the channels, will it give me more capacity or not? Can I transmit more information through this kind of things or not? It turns out it was for a long time, it was a question which is called as the additivity conjecture, that is the capacity of the product channel is the sum of the capacity of the individual channels or not. The conjecture was that no, I cannot do anything like that, which was done by Holevo. Even if I recall correctly, in 2006 he gave an ICM talk also on this channel capacity thing, in which the general consensus was that no, that this conjecture is false definitely, and I can't increase this number. In 2010 it turned out to be this conjecture is actually true, in the sense that I can send more information through the tensor product channels. It was done by a very famous paper by Hastings. Later Hastings and some other Adam Harrow and some others, Andreas Winter, they found out what is called Dvoretzky's inequality and kind of Webding bound. They showed that also mathematically also showed the same kind of things are possible, but there is one catch was there. The catch is that they used random matrix theory to construct one counter example, which came up in a very arbitrary, very higher dimensions and in a very artificial looking space, no channel actually. The question is that well, till now there was no standard way to generate such channels for which this things, I mean this additivity conjecture breaks. There was no thing. In last month, this year in May, there were 3 Polish people actually worked out a method coming from KRP's construction, whatever I told actually, from the maximal this completely entangled subspace. They used the same construction upon channels, and they found out one first constructive way to give such channels. Before that, all those things were by using random matrix theory. I think I should stop now here. Thank you. Thanks the organizers for calling my gurus in memory of my guru, and yes, questions.
Thank you, Ritabrata. It was a fantastic talk, and the stage is open for questions.
Yeah, I was going to ask if some of these results would extend to operator entanglement. I think the channel version is that one.
The arbitrary entanglement.
For example, the concept of completely entangled subspace. Can it extend to
no,
operator
I mean
entanglement?
it's a little bit of subtle. If you, what do you mean by entanglement of channel? If you say the tensor product of channels or not, no, it is not like that. It is the in your, so let me say that it's a Choi matrix is taken which has a support in the entangled subspace actually. This maximally entangled space or part of the thing has been supported there. That is how it had been constructed. But what I may also add that what you are telling may be true, but you know this kind of these channel things are these capacities are kind of norms. Some of the norms are extremely difficult to compute. So these are the objects which are extremely difficult to compute actually. Yeah.
Yeah.
If there are no questions, I want to make a comment.
Yeah.
So, in the beginning, what I was asking was like, I think more or less everybody agrees there is something weird or something counterintuitive about quantum mechanics or whatever physics or worldview it gives rise to. So, how to capture that in terms of probability theory, like based on these triads, sample space, event algebra, and a probability measure. I was told broadly there are 3 schools. Each one of them try to do one of the triads in a different way. So those who take sample space, replace the sample space by Hilbert space, etc. That is more or less standard physics school. But
Born school.
Yeah.
Born school.
Yeah. So, but von Neumann himself was unhappy with his own Hilbert space construction, and he was saying like he wants to get rid of it, etc. He tried his hand.
And came to von Neumann algebra.
Yeah. So,
but that is more thermodynamics.
Yeah. From that kind of point of view, if you try to keep the sample space same but try to tweak event algebra, and there is a duality between algebra and logic, so that gave von Neumann's quantum logic program. And the third one, if you try to tweak with probability measures, Raphael Sorkin came up with a program called quantum measure theory, quantum measures. So Sorkin was telling me that broadly there are these 3 schools, and
quantum measure theory, if I remember, actually Professor Bhatt can tell actually more.
Yes.
That I think it is there for quite some time actually. In fact, there are books also in the quantum measure theory. But the problem is that so my problem, the things becomes after some time a bit philosophical in nature. So generally I consider myself as a mathematician who likes to take the problems from physics. So the moment it comes in philosophy, I generally try to avoid that area, unless there is a strong physical reason to attack that kind of a
no,
thing. They have the thing, but I don't understand those kind of things. So I never did that. Two, that yes, there were attempts actually, and why even the measurement theory is also, there are so many measurement theories are there actually, but then again I have not managed to go further on that kind of things. As I said, that I have a very particular type of problems in my mind which I like to address. They are mostly mathematical, maybe less physics kind of.
So if we were to say that this is the approach of KRP, this is what KRP wanted to do differently with the triad?
No, because KRP never, I mean, okay, Professor Bhatt and others may have longer exposure with KRP. Whatever little I had, I felt that he was interested in the problems which are mathematically solid and sound. For instance, there are several instances, you know, in the physics, since you have mentioned all this, you also know that there are attempts for doing quantum mechanics by taking non-Hermitian observables. Okay. So, he consciously tried to avoid those kind of questions. In fact, he once told me that he encountered those things in his calculation, which he immediately junked those things. So
We'll
yeah.
talk about it.
We'll talk about, yes.
Okay, it's Sibashta.
So you know this that if you take tensor product of channels, it can enhance capacity.
Yes.
Of course, one should come up with a scheme, actual scheme. But it was
The capacity
kind of
itself requires a proper definition, which I have not given.
no, that's
actually.
fine. I mean, whether you talk about classical capacity, quantum
Yes.
capacity, whatever. But because you are having tensor product structure, you are allowing entangled state encoding.
Exactly.
So therefore, it has the you can say that because I am having entangled state encoding, it has the potentiality of enhancing the capacity.
Precisely, that was the idea was there, but then eventually people tried to do calculations in the smaller dimensions and they found out that this additivity is working.
Right. I agree with that. You know, this is a quite difficult
Yeah.
problem. So it is good that people came up with this problem. But I am saying potentially it has been there.
Yes, agreed.
So the other issue is, as far as I recall, so this dimension that you spoke about, this is maximal because it is achievable, right? This dimension,
The maximal which is achievable, yes.
it is achievable. Now there was also this idea of equally entangled subspace, where every state is entangled, but the amount of entanglement
That
is
was
equal.
the second part. I didn't go in that thing. In the same paper, it was there. I know you are taking the multipartite systems H1, H2, HD, HK, and then you are killing some of the Hilbert spaces, keeping the rest of the things with you. And then you are expecting that the states which you are taking, each one will give you that identity divided by the dimension of this kind of thing.
Yeah, yes,
Yes.
kind of thing. Equally entangled
Yes.
subspace. Yeah, because that is important when you talk about distillability and all that. If you
Yes,
take,
yes.
if you go to many copies, that will help. Okay, thank you.
Yeah, so he actually worked on that thing also, but then he didn't get some nice bound like this. Let me put it in this way. But then there are others. I think Aravinda himself also worked on this kind of situations, and he had also some results with Arul, right? Yes.
Okay, thank